In this video tutorial, we're going to cover an example of a two-way RC slab using Adapt Builder 20. And we're going to go ahead and take an example from PCA notes. We're going to take example 20.1. This is a two-way slab without beams. This is using the equivalent frame method. We're going to be using the finite element method and just compare a few of the results in these working examples. We're going to start with some of the criteria here and the geometry for the floor. We're going to model a 7-span by 3-span condition. So this is actually broken in half due to symmetry. We're going to model the entire floor inside of Adapt, and we're going to again use these characteristics of the geometry and the component sizes defined in the example. We're going to go ahead and launch Adapt Builder v20, and we're going to select the Builder RC option. And we want to make sure we have the proper settings here. So we're going to be using Floor Pro. This is used to design and evaluate elevated slabs. Under the mode, we're going to select RC, and then we're going to select US Unit System here. We'll go ahead and select OK. And we're going to first start by modeling the floor plate. So we'll start, notice here the current plane is really the first elevated plane. If I just switch this to a front view, we can see this is the current plane, and the existing column to column height here, this is 10 feet, and let's say this is 10 feet. So this is just the default kind of out of the box setting. We're going to first change that first floor to 9 feet, and we can do that from level assignment at the upper right, or we can always go to model, and we're going to go here to story manager. For the current plane, I'll just switch that height to 9 feet. We want to make sure this matches the example we're working on, so we'll switch that to 9 feet, and then I'm going to go back to the visibility, or excuse me, the home menu. We're going to go back to the top view, and I could also use the quick access tools at the bottom to switch views. So I'm now going to turn on the grid, and we're going to go to grid settings. These are also shown up here in the snap tools from the home menu. And in the X direction, we're going to have a 14-foot span. In the Y direction, we're going to have an 18-foot span. Okay, so we'll go ahead and I'm going to go back to model. I want to add a few components like a slab and a column, several columns. So we'll select column first. We know that we have 3 spans, so I'm just going to define 4 columns here. And rather than have to click on every intersecting grid, I'm just going to select this row. I'll use Control-C, Control-V to copy paste. We could also use the same tools under Modify. And I'm going to go ahead and drop 8 column lines in this direction. And these column lines will allow us to then define 7 spans. So we have 14 foot in the X direction, 18 foot in the Y direction. I can now go ahead and turn off this grid. I'll now define a slab. Now before I do that, I want to actually make sure that these columns are sized appropriately. By default, these are 12 by 12 inch columns. So I'll just select all, and in this property grid, I'm going to change this to square, and we'll go ahead and just enter 16. That'll change the column size. For slab, I want to go ahead and just model this to the outside face of the columns. And so in order to snap on that corner, I need to turn on snap to endpoints. I can use again the quick access tools, or I can go back to home, use the snap tools here. And in conjunction with snap to endpoint, I'm going to turn on snap to vertices of components. And you can see we'll just snap on those component or those column corners, select enter, and now escape, and I've entered the slab. Now this slab, in the example that we're using, this slab is going to be 7 inches thick. So they're trying a 7-inch slab here. And they base that on deflection, some of the predetermined deflection limits per the code. And also they make a check of punching shear as well. So we'll make sure that this is set to 7. Select that. That changes the slab to 7 inches. All right, we're now going to define the material properties. So in the example, we have 4,000 psi for slabs, normal weight, 6,000 for columns, and then 60 ksi for the reinforcement. And so we'll go up here to criteria under concrete. I'm going to add a new concrete material, and we can say maybe this is actually columns. and we could define this as slabs, but we'll go ahead and change this to 6,000. And once we've done that, we can then assign our components. So the slab, I can either double click to launch the properties or single click to just enter the material here in the property grid. So this material for slab is concrete 1. That's by default already set. I'm now going to just select everything and then press Control and unselect or deselect the slab, and now I'm left with my columns, and I'll change that to column material. So those are the column materials. I also want to jump over here from concrete to rebar, make sure that this is set to 60 KSI. And for my analysis and design options, I want to make sure I have the proper support condition at the far end of the columns, and that's going to be fix. So we're going to be working today just as a single level model, one level with columns below. So for single level support conditions, we're going to say that this is fixed at the base, and that is really the model setup. Now for this particular example, we're using PCA notes from 3.18 version 11. So we're going to select the design code to match that. We have ACI 14 and also 19 as well, but we'll just select 2011 here. And once we've done that, we basically have the same model that has been defined here. We're going to add some loading now. There are no edge beams. There's no edge loading. We just are going to have a 20 PSF dead load. This is a superimposed dead load, and a 40 PSF live load. So let's go ahead and do that. I'll select the slab, go over here to loading. Loading is always cumulative. I can either manually input the load using these general load inputs. So if I select patch load, I would snap on points that define the patch load region, or also known as the uniform load region. Or if I select a slab, I can then enter through a wizard. So we'll use the wizard. There's two predefined load cases, dead load and live load, so we don't need to set those up in this case. This is going to be 20 pounds per square foot, or 0.02 KSF, and then I'll just do that again for my live load, and the live load here is 40 pounds per square foot unreduced. If you needed to add additional load cases, we could always come here to the load case manager and add additional load cases here. For load combinations, the example is evaluating strength, dead, and live. So when we select a load or a design code, the program will add some just default gravity combinations here. And we're really going to be comparing a few results really just to the strength combination. But if you have service combinations also set up, the program will then add reinforcement to meet minimum reinforcement requirements as well as strength requirements. And we need these strength combos also to evaluate the punching shear. So make sure that that's looking similar to what the example shows. I'm also going to go ahead and add, in addition to these combinations, this is not in the example, but we want to maybe add some cracked and long-term deflection combinations. So if we go ahead, and this is an example of how we would add these manually, we're going to go ahead and select the option for cracked deflection, and we're going to say crack 1 is really cracked sustained. We'll say crack 2 is really cracked total. So we're going to evaluate the slab for the sustained loading, whatever load factors we assign. And in this case, we're going to say sustained is the dead load. Notice self-weight is automatically included here. And then the live load, I'm going to say 30% of the live load is sustained. The total service load is just 1 times all of the load cases assigned. And the next thing we're going to do is add in a couple of long-term deflection combinations. The long-term deflection analysis and design option type allows you to combine results of other combinations that have been defined. So we're really combining or enveloping combination results in the program. And so we'll go ahead and select 2 of those. This one I'm going to call live load increment. So we might want to evaluate the incremental live load, or the difference between total and sustained, for example. And I'll just say this is really 1 times the cracked total minus 1 times sustained total. And then the long term, we'll call this long-term deflection. this is going to be, this is fairly simplified, but we're going to say that this is going to be 1 times the live load increment, which is the balance or the difference between these two, plus 3 times the sustained load. So this is going to be the instantaneous sustained deflection plus, let's say, creep and shrinkage, when we'll just assume the multiplier is 2. So 3 times this load combination here. And this gives just an example of how we can use these combos to not only evaluate cracking, but then to combine those results for the long-term deflection. And we'll go ahead and close that. All right, our next step is going to be to generate design strips. Now, in the example, we evaluate the equivalent frame. So we're really just evaluating one single frame in the Y direction. And this frame is then taken using the total static moment and dividing that into different multipliers or factors associated with span condition and then middle and column strip. We're going to show this as a full tributary design strip first, and then we'll show how you can convert that to actual column and middle strips as defined in the program. And we're going to kind of skip down here. Here's our punching shear check. We're going to come back and confirm that. But if we look at some of the results here, we'll go beyond the moment distribution, or the moment distribution for the frame analysis. And we're going to skip down and really just look at what is the total moment over a particular location in the. And we can see that right here. So we're going to be comparing our results really to this moment diagram for that internal frame. And you can see these are cutoff moments as compared to centerline moments. This is at face of support or wherever they're evaluating the moments at for purposes of design here. So we'll go back to our example. And in order to generate these strips, we need to generate what are called support lines. So we're going to jump over here to floor design. And we're going to be using the strip modeling. I'm going to go ahead and use the dynamic editor. And for the dynamic editor, we're going to be working in the Y direction first. And I'm just going to pass this through a frame line and press enter. And we can do that for each unique set of columns or frame line. And you could also go ahead and close that. And because these are all the same, I'm going to use an option here. So I can use Control-Shift-C, where I'm actually going to take and we're going to copy this from this reference point over multiple times. And this might be a little bit faster using one of these tools built into the program. We're going to also do this in the X direction. So we'll go back to Dynamic Editor, and I'll use the X direction. And here we're going to use this for all of the frame lines in the X direction. So we'll do that. We now have our X and Y design strips. And the way that this works is that the program for each direction, it will essentially scan the slab in either direction and find where the adjacent support line or a slab edge exists, and then it will break this into a tributary. So this becomes the full tributary for this equivalent frame. And this is one particular method that we can use for this example. Another thing that we could do, which I'll show as a different step after we review these results, is break this into column strips and middle strips. Now, in order to design these strips, we can select the support line, and we can see this has some properties associated to it. The governing criteria is a two-way slab. There are inputs for how many design cuts we want along the span. The spacing here maximum is 2 feet. We need a minimum of three sections, and there are several design characteristics that you want to make sure you go through and assign to these support lines. These are being designed as RC slabs. One such characteristic might be cover. In the rebar cover, we want to go ahead and define that. So under this rebar cover option, for a two-way slab, we're going to say the cover, and this is from extreme fiber to the face or to the outer edge of the reinforcement. We'll say this is 0.75 inches for this two-way slab criteria. Once you set up your strips, now we're going to go ahead and generate the design cuts. And when we do this, the program is actually generating strips in both directions. That's why when we turn that on, when we turn both directions on, we see kind of overlapped design cuts. If I go ahead and turn that off using this visibility tool, I can isolate X direction, and we can colorize the actual strips themselves versus the Y direction, and this shows us those strips in the Y direction. All right, we're now ready to analyze the slab. So let's go ahead and just turn off the strips for a moment and the tributary regions, and we're going to go to analysis, and we're going to want to mesh the slab. Now for the mesh, I'm going to use a 2-foot mesh, and I'll use a uniform versus a sparse mesh. This is a little more organic in nature. This is more uniform in terms of the element and the arrangement. We're going to turn off node consolidation. This is an option used to consolidate multiple physical nodes into a single analysis node. So we want everything retained as it is for the comparison of the example. I'll go ahead and mesh the slab. Once we mesh the slab, we're going to go ahead and execute the analysis for the combinations that we defined. And this uncracked just means that we're assuming that nothing here is cracked for this first run. Okay, and the analysis is complete. So the next thing we're going to do, I don't really want to see these analytical elements, so I'll go up here to the visibility, and I can just turn off the shell elements for the slab, or turn them on if you want to see them. So there's ways to control the visibility there. The next thing we'll do is we're going to come back and turn on our strips, and I'm going to now, we've already generated them, we're just going to now go ahead and process them. We want to design the sections. All right, we'll select yes to save those results. And now we can go ahead and take a look at some of the results along these design strips. So let's isolate just the Y direction, for example. Over here in the result browser, we want to go ahead and select the combination or envelope of combinations that we want to display on screen. So we're going to select strength, and we're going to go ahead and select strength dead and live. This is the combination we're going to compare with the example. Under analysis, we're really evaluating design sections, or we're wanting to review the results of the design sections. We'll go to actions and we'll select bending. And this will show us the bending diagrams for this particular combination. And I want to display all design cuts numerically, so I'll select numerical display. And now we have our results. So negative moment on the perimeter exterior column is negative 24.3. First interior moment is around 47 kip feet. And if we just compare that to the results here in this example, we have a design moment about 32, 44, 67, 60. And we're looking at 24, 47, 61, 56. So you can see the results here using FEM are pretty close to the results using the equivalent frame method. And again, this is based on an entire tributary. So this is the fully integrated design cut. It's using nodal integration along the path of this design section. And ultimately, we want to use those actions to then design the slab. So this is really just showing us the demand side. If I go to, for example, the reinforcement, we can see for this combination, the program has calculated reinforcement. So I'm going to go ahead and select calculated required. This is the reinforcement required for each location. So you can see at the midspan we need about 2.34 square inches. Here we need 1.06, 2.7 at the interior column. And those numbers again can be checked against the results here in the example. And we have pretty good correlation between the two. So for example, for the area of steel at exterior column, the moment in the equivalent frame method was slightly higher, so we get about 1.28 square inches of steel. They go through and check the amount needed for the unbalanced or for the transfer through flexure at the column joint. And if we look at the required amount here, we have a little less here just because our moment's a little bit smaller for this particular condition. But this shows us the required reinforcement along the paths of the design strips in terms of the area of steel. I could also toggle this also to the X direction and see those bars there. There are other settings here that allow us to see what's actually been provided. So this is what's required at every design cut. If I go to provided I need to go ahead and generate the plan first. So let's go ahead and go up to floor design. I'll calculate the rebar plan. I could do this for envelope of service strength, or pick a combination, and we'll pick that strength dead and live combination. You can see the program actually is going to show us the rebar on screen. Let's go ahead and hide those design cuts. Here we can see the reinforcement along each of the strips. Now this is showing us the reinforcement in X and Y directions. This is exportable as a DWG or DXF. It's also exportable to Revit if this model was initiated in Revit, or if the user exports this to Revit as a model, both geometry and reinforcement. So this reinforcement can then be manipulated on screen for the presentation, and we can go to this option for Rebar Display Manager. Maybe we just want to look at the bars in the Y direction, so we'll go ahead and isolate the Y direction. You can see in this case we're using bar sizes as set in the rebar size and material. So for two-way slab, we're going to use a number 4 bar, let's say 4 top and bottom. And here we have, let's try that one more time. I'm just going to refresh the results here. Okay, and so here we have 18 number 4 bars, 18 number 4 bars. And there's one additional check that the program is making. These bars are actually distributed over a width equal really to the design strip. So we calculate the total requirement of area still and just distribute that over whatever the design strip equals. There's an additional check made, which is shown here under Rebar Roundup, and this says if the spacing of those bars does not meet these two minimums, the program is going, or maximums, the program is going to limit the spacing to this criteria. If the user wishes, they can turn that off, so really the outcome is whatever is calculated for strength or service. But this particular check may be affecting the total number of bars that is presented here on screen. But you can see that the bar layout for top and bottom still. There's input within the rebar criteria for cutoff lengths, extensions over columns, extensions in span, centering of bars in span, and so on. But this is just one such example. If I go back to the result browser, which we showed earlier, I'm going to go over back to floor design and turn on my strips in this direction. And I'll hide the rebar. Let's turn the rebar off. And we're going to go ahead and now calculate the provided area of still. So this is really what's provided along the support lines. Okay, so we see provided reinforcement. And then last thing we'll show here with the result browsers, we're going to go ahead and show investigation. So we might want to see the moment capacity and demand on the design strips. This might be more easily shown in the X direction, so we'll go ahead and switch over to X. And I'll show moment capacity with demand. You can see that the blue is the enveloped capacity for negative bending, and then the green is positive bending capacity, and the gray is the envelope for strength demand. And we have plenty of room here with this slab in terms of capacity. This really just says that the minimum reinforcement controls the design of this slab. Now earlier we made a comment about middle strips and the ability to model those directly in the program. So we're going to go back to our floor design. I'm going to just delete out the design strips. We still have our support lines, but we want to generate now middle strips based on our input of column strips. So we'll go back to the dynamic editor. Under middle strips, we're going to create middle strips. The program adds middle strips here, and the middle strips now will be used to define and displace part of that full tributary that we previously modeled. The user has the ability through the dynamic editor to allocate a percentage of tributary either side of the column strip using the option here for limits. So you could say, well, I want to use 25% to each side of the column strip and then fill the rest in as a middle strip. We're going to just let this naturally take place. In other words, the program, half of the tributary will be taken by the middle strip, and then 25% just by default is taken by the column strip. So we'll turn that back off and set that to none, but that is an available feature here. And we'll generate our design cuts again. And now we have, if I isolate X or Y, you can see we have middle strips and then column strips. And so we'll go back now. We've basically recreated strips in the model, and I'm going to redesign them based on the first analysis that we ran. We don't need to run the analysis again. We're just now more granularly going ahead and generating rebar for column and middle strips for the slab. And the outcome is presented similarly to the first example, in the sense that if I calculate the rebar outcome for any of the combinations selectable here, you can see now it's actually reflective of both middle and column strips. So isolating this again for more clarity on screen, we'll go to Rebar, Display Manager, and you can see the allocated rebar for each position. And then finally, will show a quick example of punching shear. I'm going to go back. I'll turn my rebar off. I'll also turn my floor strips off. And under punching shear, we could go through and set up our shear design requirements here. We have another video that kind of details this in terms of what all these settings mean. There are some global settings, and then there are also several local settings to columns. If I select the columns, go to punching shear, we have additional local settings for those columns. But ultimately, we're checking this based on the selected code ACA 318, so we'll just use the default settings, and I'll execute the shear check. And then for that strength dead and live case, or for the strength envelope, if I go ahead and select punching shear, you can see that all of the columns here, we can see all of the columns here are shown as OK. So this is just a simple status check. If we go to stress ratio, this gives us more information. And you can see here the text is a little bit large, so we can control that in our view settings and our columns. I'll say the text size we're going to cut in half there. And this shows us the controlling stress ratios for bending about axes separately. So this just shows us the controlling critical section that produces the greatest ratio, the condition, whether it's a end edge, corner, or interior condition, and this actually reports the effective depth used for the check at the first critical section. And then finally, if there is any reinforcement needed, it would show that, but these are all shown as acceptable, which in the example we saw that the punching shear reinforcement at the start of this example was acceptable. That was shown here. This is okay. So this is in correlation with the example in terms of the punching shear. The last thing we're going to do is look at the crack deflection, which we introduced on top of the example. So in order to produce a crack deflection result, we have to make sure we've analyzed, number one, we've also designed the sections. So here we're going to, I'll just redesign them as a step needed to enter into the crack deflection check. All right, and then under analysis, we're going to select crack deflection, and the program goes through the crack deflection check, and then there's graphical reporting that we can access to check cracking. So that's completed. If we go back over here to loads, you can see we have crack deflection combinations. We actually check the slab for each crack deflection combination using I gross and then I effective. So as an example, if I look at the result for slab deflection, we'll go ahead and turn on that contour map, and you can see the deflection here is about 0.11. This is for the uncracked state. If I go ahead and now check it for the use of I effective, you can see there's a little bit of a change there in the deflection. It's hard to detect because there's probably not much cracking happening at this condition or this load case, but we can go further and check additional results to confirm that. So if we go back to analysis for this crack deflection case, we can see under actions, we can check the reduced rotational stiffness about the x-axis and then about the y-axis. So we're losing about 30% stiffness bending about x over these interior columns, and this is the y check. So in the Y direction, bending about Y, that's our shorter direction. There's no cracking. In the longer span direction, there is some cracking. And so that affects those deflection results slightly that we saw earlier. And then finally, if we wanted to produce the long-term cracked deflection check, we can check this cracked deflection long-term and produce a result for that deflection on screen. So the uncracked total load is about 2.29 inches or 0.11 inches. The cracked long-term is about 0.3 inches. If you have any questions about the program and its capability for doing two-way RC slabs, please contact us at adaptsupport@resa.com. Thank you.